To address the limited sample issue faced by data-hungry machine learning methods, as we mentioned in the last lecture, we examined several approaches suitable for limited sample scenarios. The first one is ARMA. ARMA model treats a time series as a linear stochastic process composed of two parts, past observation and past random disturbances. Compared with machine learning methods, ARMA models have strong interpretability, far fewer parameters, and very low training and inference cost, which makes them attractive when data are limited. Mathematically, the ARMA model predicts the next state as the weighted sum of past values and past noise terms. Here, the A coefficients represent the autoregressive part, while the B coefficients weight the moving average noise terms. Notice that once we move beyond the historical sample window, the true noise terms are no longer observable. As a result, when all liked terms are replaced by recursively predicted values, the ARMA model asymptotically degrades into a pure linear autoregressive model. In practice, this means that the moving average component no longer contributes during non-horizon prediction. The recursive forecasting process is similar as before. Now, we examine the numerical performance of a linear AR model with a lag of 4. Although the linear autoregressive model is stable and data efficient, it struggles to capture underlying trends when the lag window is short. This limitation stems from the overly simple linear structure, which is insufficient to represent nonlinear dynamic patterns commonly present in real power node time series. This motivates the use of slightly more expensive models that still remain sample efficient, which we will discuss next. We now introduce kernel ridge regression based autoregression, or KR based AR methods, which serves as a bridge between the linear AR models and the data-hungry machine learning methods. Compared with linear AR or ARMA, KR-based AR enhances modeling capability by introducing nonlinearity through kernel mappings. Compared with deep learning models, it performs well with limited training samples and admits a closed-form solution, leading to no training cost and stable performance. The idea starts from ridge regression. The output is modeled as a linear function in a feature space, y equal to phi times w. The model is trained by minimizing a regionalized least square objective, which yields a closed-form solution. However, directly computing inner product in the high-dimensional feature space is expensive. This motivates the use of kernel track, where inner products are evaluated implicitly through kernel functions. We now briefly explain kernel ridge regression. By the representer theorem, the optimal solution lies in the span of the training data, though the weight vector can be written as w hat equal to phi transpose times alpha. Substituting this into the ridge regression solution and applying the matrix in lemma, the problem is transformed from the primal form to the dual form. At this point, all inner products appear as phi times phi transpose can be kernelized as a grammar matrix K. This means the inner products in high-dimensional feature space are computed implicitly by the kernel, avoiding explicit feature construction. The dual coefficients admit a closed-form solution, and the final prediction becomes as below. We now extend KR to multiple kernel ridge regression, or MKR. The key idea is to construct a composite kernel as a weighted linear combination of several base kernels, allowing the model to capture different types of structures simultaneously. For example, we can combine a Gaussian kernel, a periodic kernel, and a polynomial kernel with non-negative weights. The Gaussian kernel captures highly nonlinear local patterns. For most scenarios, we only use the Gaussian kernel is enough. This is the most general KR-based methods we introduced before. And the periodical kernel explicitly models seasonality and cyclic behavior. And the polynomial kernel represents global interactions with controllable complexity. While MKR improves the expressivity of the model, it also introduces more parameters. As a result, there is a trade-off between model expressivity and the amount of data required for training. Here, we present the numerical tests for the KR and MKR under both high similarity and no similarity source target scenarios. Starting with the KR using a Gaussian kernel, we observe that in the high similarity case, the predicted curve closely follows the true load profile, capturing both the magnitude and short-term variations. In the no similarity case, performance slightly degrades, but the overall trend is still well preserved. Next, we consider an MKR, where Gaussian and polynomial kernels are combined. The results show a very similar behavior in both high and low similarity cases, with marginal improvements in capturing smooth globe trends. This means for this case, the KR model is good enough to use, and the KR model also have fewer parameters, have a lower training cost to avoid overfitting. Overall, for short-term day-ahead forecasting, KR and MKR exhibit comparable performance. Among all the sequence-to-point methods introduced earlier, these KR-based approaches achieve the best accuracy, especially under limited training data conditions. This highlights their strong balance between model expressiveness, data efficiency, and robustness in limited sample scenarios. For the next lecture, we will introduce to the geometrical constraint methods for the power forecasting. That kind of method is also powerful to learn the vector field in the dynamic equations.